Here we've got an example that asks us to find the equation of a tangent line to the graph of 1 over x at x equal 1. And so the idea is, we know that 1 over x looks something like this. So maybe that's 1 there, and I didn't make it curved very well. But anyway, I want the tangent line at this point here. So we can say it's some sort of negative sloped line that I want to find. But I only have the one point. That single point of tangency is all I've got. And I know that to find the equation of a line, I need a point, so I've got that, and then I need the slope of the line. And that's where the derivative comes in. So remember when we did the preview of calculus, we saw that that slope, when we were approximating it, ended up being the limit as x approached a of the difference in the y coordinates. So that would be f of x minus f of a. So that's my y coordinates, where I was using these secant lines to approximate it. So I had this point x, f of x, and then this point, in this case it's 1, f of 1. So it would be the difference in the y's over the difference in the x's. So that would be x minus a. Anyway, so that's how we find the slope. And so our derivative is the natural way to look at that. So I'm going to just say my slope is going to be my derivative evaluated at 1, the point of tangency. So that's I need the slope and I need a point. Well, my point is my point of tangency at x equal 1 and my y coordinate, which is f of 1. So let's go ahead and get that. That's just simply going to be 1, 1 when you plug into this function. But let's go ahead and calculate the slope then. The slope is the limit as x approaches 1. So I've got either option, but I'll go ahead and use this option because it looks more like my difference in y's and difference in x's. But I'll probably calculate this limit both ways just to practice that using both definitions. Anyway, so this is going to be f of x minus f of 1 over x minus 1. And so for this problem, that's going to be the limit as x approaches 1. F of x is just 1 over x. F of 1, that's the y coordinate here, that's just 1. And then that's divided by x minus 1. So that's going to be the limit. Well, so what do we do in this case? There's no factoring to do, but there's fractions involved. So this one's going to be, I'll use the common denominator of my little fractions, which is just this one fraction. And I'll clear out the fractions by multiplying the top and bottom by that. So in the top, when I multiply by x, it's going to cancel out the x's here, just leave me with a 1. And here it's going to leave me with a minus x. In the bottom, remember, I'm trying to get this x minus 1 to cancel. That's the whole point. So there's really no reason to multiply it out. I'm just going to leave it as x minus 1 times x. And I have a 1 minus x over x minus 1. And if you remember in a previous video, this can be, I can factor a negative 1 out of this and turn this thing around. The point being that I can cancel these not as a 1, but as a minus 1. So this will become the limit as x approaches 1. Once I get that canceled, I'll just replace that top one by minus 1 over x. And so now I no longer get a 0 in the denominator, because when I let x go to 1, the denominator's going to be it's going to be 1. So this is going to be minus 1 over 1. So this has a slope of minus 1. So to write the equation is no big deal. Now that's kind of an afterthought, but to write the equation, you get y minus the y coordinate of your point of tangency equals your slope, x minus the x coordinate. And if you want to simplify it and solve for y, you get y equal minus x. This will be plus 1, and then you're going to bring that over. So anyway, you can simplify. That's the equation of this line that's tangent here to this curve. Okay, so let's do that limit one more time. Let's do it the other way, using the other definition. So the slope could have also been calculated by taking the limit as h goes to 0, f of 1 plus h, that's my point of tangency at 1, minus f of 1 over h. Now, that doesn't look quite as much like a difference in y's over difference in x's, but this certainly is a difference in y coordinates, right? It's my function evaluated at one value minus my function at another. Those are two y coordinates. Down here, it's not clear that this is a difference in the x coordinates, but the x coordinates are 1 plus h and 1 in my formula here. And so if I subtract those, 1 plus h minus 1, I do get h. So this is the difference in the x coordinates, the corresponding x coordinates that are used here. So this is the same thing, it's just a different way of looking at how I'm getting that tangent line. Instead of using x's for my notation when I'm doing my secant lines, what I'm doing is I'm just kind of saying I'm going to go a little bit past 1 and get my second point. And then I'll let the h kind of generate. So this is okay, it's all crammed together here, but let's pretend that's 1, and this is 1 plus h. And then I'm going to let the h go to 0, which will force that point into 1. So it's the same sort of idea. Anyway, let's work this out. We get the limit as h goes to 0. Here I'm going to have 1 over 1 plus h minus 1, and in the denominator I'm going to have h. So it's the same requirement here. To simplify this, your best bet is going to be to clear out that fraction, and so I'll do that by multiplying the top and bottom by 1 plus h. Can't make an h, sorry. So when I multiply the top by 1 plus h, just like in the previous manipulation, I had this canceling, leaving me with a 1, minus multiplying that by 1 plus h, I get 1 plus h. And the parentheses are important here because I need to subtract the whole thing. Don't just say minus 1 plus h without parentheses, because you might mistakenly miss something. In particular, when I actually do clear the parentheses, here's what I get. I get 1 minus 1 minus h. That negative has to be distributed. And so if you'd just written this as minus 1 plus h, you might not think to distribute that minus. So be sure you do that, otherwise you're going to miss the sign. Well, the 1's cancel. I get the limit as h goes to 0 of minus h over h. Well, I can cancel that as well. The limit as h goes to 0 of simply minus 1. Now if there's no more algebra to do, I can take this limit. Well, it's a constant, and the limit of that constant is minus 1. So I still get my slope to be minus 1. Very similar manipulations. There's a little bit different result here towards the end where I had that parenthesis. So there's not necessarily one that works better than another, or there's no way to tell up front which of these two derivative formulas is the best to use. So we'll use them off and on. We'll use each one. Okay, so that's one interpretation of the derivative. You can always think of the derivative as giving you slopes of the tangent line. So when I have a graph of a function, there's always this notion of a derivative, this geometry behind it is the derivative is giving me the slopes of these different lines at any point. So we just did it at a single point, but every point where that limit exists that we have to calculate, at every point there's this tangent line attached. So all along here there's tangent lines attached. So that's one way to think about when we just in the abstract calculating derivatives in your mind. One way to think about what you're doing is you're finding the formula that gives you the slopes of these different tangent lines.